Here's a crazy thought for you. What if you could know if you've seen something before without actually having to remember it? I know it sounds like some kind of magic trick, but it's the real idea behind one of the most clever tools in computer science, the Bloom filter. Today, we're going to dive deep and explain just how this incredible, paradoxical data structure actually works.
So just imagine for a second, you're building the next massive social network. A new user wants to sign up, right? How in the world do you check their desired username against a list of a billion others and do it instantly? And let me tell you, this isn't some abstract problem from a textbook. This is a real-world headache that engineers at huge companies deal with every single day.
Well, the solution is it's beautifully counterintuitive. What if you could build a system that remembers every single item you've ever shown it, but without actually storing any of them? It sounds completely impossible, I get it, but that is precisely what a Bloom filter is designed to do.
Okay, so let's frame this properly. We're going to call it the billion item problem. And the real challenge here isn't just about finding a way to store a billion usernames. The real trick is being able to ask, hey, have I seen this before? And get a useful answer back in like a fraction of a second. And here is the absolute key shift in thinking you have to make. For these gigantic systems, the most expensive, time-consuming thing you can do is often search for something that isn't even there. Think about it. A database might have to grind away scanning a massive index file on a slow disk, all just to come back and say, nope, sorry, not here. What if we could just avoid that entire painful search almost all of the time? Now that would be a huge win. And this is exactly what leads us to the solution, a probabilistic shortcut. See, instead of giving you a simple binary yes or no, the Bloom filter offers a much more nuanced and, as it turns out, an incredibly powerful set of answers. Okay, so what is this thing officially? Well, the formal definition is a space-efficient, probabilistic data structure that tests whether an element is a member of a set. Now, the two most important words in that whole sentence are space-efficient and probabilistic. That's where all the magic happens.
And this brings us to the core trade-off. This is what it's all about. A Bloom filter only gives you one of two answers. If it says no, it's a guaranteed, ironclad, 100% certain no. The item is definitely, absolutely not in the set. We call this having no false negatives. But if it says yes, it's more of a probably yes. There's a small and, very importantly, a manageable chance that it could be mistaken. And that's what we call a false positive.
So you're probably wondering, how on earth does it actually pull this off? Well, the best way to really get it is with a simple analogy. I want you to imagine we're building a machine that turns any piece of data into a unique pattern of light switches. Okay, here's how it works when we add something. First, we start with a really long array of bits. Just picture a huge panel of light bulbs, and they're all switched off. Now, say we want to add an item, like the word apple. We take apple and run it through a handful of different hash functions. Think of them like unique magic markers. Each marker points to a specific light bulb on our panel. So we just go to those positions and flip the switches to on. And that's it. Now here's the critical part. Notice what we didn't do. We never actually stored the word apple anywhere.
All right, so how do we check for something? Let's say we want to see if the word carrot is in our set. We do the exact same thing. We run carrot through those same magic markers. They point us to a set of specific light bulbs, so we go and check those bulbs. Now, if even one of those light bulbs is still off, we know for a 100% fact that carrot was never added. It's impossible. But what if all the lights it points to are already on? Well, then we say it's probably present. And why only probably? Well, because it's possible that some other words we added, like apple and banana, just by pure coincidence, happen to turn on that exact same set of lights.
And this is where the real engineering comes into play. That chance of a false positive, that coincidence, it's not just random luck. It's actually a variable that we, as engineers, can control with incredible precision. We basically have three main control knobs to play with. First, there's M, which is the size of our bit array, how many light bulbs we have on our panel. More bulbs means fewer accidental collisions. Then there's N, which is how many items we plan on adding. And finally, K is the number of hash functions, our magic markers. By tweaking these three knobs, we can dial in the filter's accuracy to exactly what we need. And this really gets to the core philosophy of what makes a Bloom filter so powerful. That error rate, it's not a bug that needs to be squashed. It's a design parameter that you get to choose. You get to look at your system and decide how much error is acceptable, and then you build the filter to match that exact tolerance.
So, let's make this super concrete with an example. Let's say we need to keep track of 1 million items, and for our application, we're totally okay with a 1% false positive rate. That's our target. Well, you can do the math, and it'll tell you that you need a bit array with about 9.6 million bits, and that the optimal number of hash functions or markers to use is 7.
So what does 9.6 million bits actually translate to in terms of memory? Just about 1.2 megabytes. That's it. Let that sink in. That is an astonishingly small amount of space to effectively remember 1 million different things, even with that tiny error rate. It's incredible.
Okay, so this is all really cool in theory, but where do we actually see this stuff in action? Because let me assure you, this isn't just some neat academic concept. This is a workhorse, a fundamental building block of modern systems engineering.
The answer is they're everywhere. Seriously, databases like Cassandra and Bigtable use them to avoid that slow, painful disk lookup for a key that doesn't exist. Your web browser? It probably uses one to quickly check if a URL is on a massive blacklist of malicious sites. Big data systems use them to spot duplicate records in enormous streams of information on the fly. In every single one of these cases, getting that super fast, definitely no answer is the name of the game.
But of course, as with anything in engineering, there's no such thing as a free lunch. To use Bloom filters the right way, you absolutely have to understand their limitations. The best way to see the trade-offs is to compare it to a standard hash set. A hash set gives you a perfect, exact answer every time, but it uses a ton of memory because, well, it has to store every single item. A Bloom filter, on the other hand, is probabilistic, uses a tiny amount of memory, but, and this is a big one, in its classic form, you can't delete items. And why not? Well, think about it. If you go and flip the light switch back to off, you might accidentally be erasing a crucial piece of the puzzle for some other item that also happened to use that same switch.
So let's just clear up a few final common points of confusion. First, as we just said, no deletions in the basic model. Second, throwing more hash functions at the problem is not always better. As we saw, there's a mathematical sweet spot, an optimal K. If you go past it, your error rate actually starts to get worse. Third, if you add way more items than you originally planned for, the filter just gets saturated with ones and its accuracy completely tanks. And finally, the quality of your hash functions themselves is absolutely critical. Bad hashes mean lots of collisions and a high error rate. And all of this brings us to the final, and I think the most important question of all. The real genius of the Bloom filter isn't just the clever data structure. It's the mindset it forces us to adopt as problem solvers. It makes us ask the crucial question. For the problem I'm trying to solve, when is probably good enough? When is it the smart move to trade a tiny sliver of absolute certainty for a massive, game-changing gain in speed and efficiency? Answering that question, well, that's what great engineering is all about.